All right, good morning. So this is our new classroom. I had to fight hard for this class, we'll see. Hopefully it's going to work out better. One thing I'm noticing is that there's no clock here, so in the room. So you should be vigilant. I don't like going over time. So we have a couple things to do. One of them is I want to display these three different methods of proof. We had 4 of them, remember, and I said we're going to first look at 3 of them. I did 1 of them. On Friday, I want to exemplify the other 2 proof methods using this rather straightforward arithmetic statement also. Then we're going to discuss certain operations we can do with relations. And that's going to be it for today. I wanted to discuss perhaps further questions or comments about the first problem sets. So, yeah, I guess you'll find your way. One of the things I want to say is, at the beginning of the 3rd section, namely what to submit, the section where I list all down, I listed down all the problems. I have this statement: when tackling statements in 3210, follow these 4 steps, and in no particular order. Okay. How to approach statements. In 3210. Right, so the first statement is, first step is, well, I guess I say in no particular order, but there are 4 distinct sort of processes or procedures that I can sort of think about. So, assess the truth of the statement. Remember, I told you in the problem sets there are going to be all these neutral statements. Question?
No, I was just
okay. Yeah, I'd rather you talk to me. Okay. Yeah. So I told you in the problem sets I'm going to state the problems as neutral. It's not going to be clear if it's correct even. And obviously, if a statement is wrong, you're not going to be able to prove it. Or maybe you think you have a proof, but it's not going to be quite the statement. Okay, so that's going to be an important thing. Now, to help you with that, I also make certain comments about this. Now, what are the sources of these problems? Some of them are from the textbook, okay? And so I use AI to basically scrape all the problems and sort of restructure them, rephrase them, maybe neutralize them and stuff like that, and sort of represent to you. And so this is where looking at the textbook would come into play and would be helpful. And so here, for instance, I mentioned something. Some problems, I say, may be variants of theorems or exercises from the textbook. And that's also somewhat of a dubious matter. What is a theorem exactly, and what is an exercise? You're going to start seeing in the textbook, for instance, they're going to say theorem, but then proof is going to be exercise. But then, is it an exercise or is it a theorem, right? And so, ultimately, for our purposes and for your purposes, insofar as something is an exercise that I give in class, or it's something that I explicitly state as a problem in a problem set, that means that you need to be able to know how to prove it. Okay, so problem sets and lectures override every other resource is what I'm trying to say. And then I say, for instance, part B of problem 1 below is a paraphrase of exercise 7 of section 1.1 in the textbook. So some like looking at other resources, for instance, the textbook, to get an idea, okay, how to approach this problem, any problem in general. But, some people don't care that much about, what other people did before. they say, oh, this is too cumbersome for me. I'd rather just think about it myself. These are both valid approaches to trying to solve problems and get an idea. And I say, going forward and possibly for the rest of this problem set, such correspondences will not be mentioned. Okay, it will be up to you to locate them if need be. So I use this textbook and I use other. I look at other textbooks of similar level and I come up with my own problems as well. And this is the sort of source of all problems. Assess the truth. Okay, this is the first step. Another item is building a case. Now, this class is all about, formalisms and everything, but ultimately, it would be misleading to think that you sort of look at it, you look at the statements and you immediately sort of see that it is true or false, and then you start writing a proof. Often it doesn't work like that. You need to do some experiments. Now, this is not sort of physics, or this is not a positive science in a sense. It's not an experimental science or empirical science. So our experiments are calculations, okay, simple cases, things like this. Now, just because you figure out, for instance, if you're trying to prove this, oh, what if n were 5? Then 3n plus 7 would be 15 plus 7, which is what? 22. Oh, that's even. Okay, so that would be part of building a case. That's not a proof. The proof is not, so the statement is not saying anything specific about the number 5. But you can test out the validity of the statement, at the very least. Now, in this case, this is not too scary looking, this statement. Okay, but we're going to get into, we're going to start talking about more and more complicated statements, and it's going to be an important thing to be able to do, to take this complicated thing and sort of turn it into simpler cases, just to get the sense first. Construct a proof. So this is where the formalism comes into play. So you sort of first figure out if you have a case. Then you sort of try to, so these two are somewhat related, of course. Often you're going to try to build a case to even figure out if your statement is correct, right? And as you're doing these two, imagine you're sort of like a lawyer and you're sort of trying to build a case. You're sort of trying to figure out if you have any standing, really. But then you go to courts, and that's where the proof part comes into play. Now you need to play the game of formalisms and everything. That's a different matter. And part of the reason why I spent this much time on logical stuff and set theory and stuff like that, so that you have some idea as to what type of sort of formal shenanigans you have to be playing. Okay? And then going further, perturb the statement. And what do I mean by perturb? I mean vary it a little bit. See anything else can be said. For instance, this statement says if n is odd, then 3n plus 7 is even. You could say, does it work the other way around also? Right, this was part of this Wason selection experiments. Part of it is, being able to argue logically. But another part is, well, just because this statement doesn't mention anything about equivalence doesn't mean that equivalence doesn't hold in general. And then maybe you can say, oh, how about if I were to look at all integers instead of only positive ones? Things like this, okay? And all of these somehow, oh, another perhaps thing that is very important is, some of the statements in the problem set are going to be false. For instance, in the first problem set, there is one that I put specifically as false. One thing you can do is, one of the important things to be able to do is noticing that something is false, but then also figuring out, or being able to figure out, how we can correct the statement. Just because a statement is wrong doesn't mean that you're done. Now your job is What is the right version? Okay? So these are all what I mean by perturbation. And this is how sort of people come up with new math ultimately. Okay? They look at something, a statement, they know it is false, for instance, but they really want it to be true. And so they redefine everything so that the statement is correct now. Or they look at a different version of it and stuff. So these are sort of like abstract statements. As time goes by, I hope it's going to make a little bit more sense. Okay? And of course, when I say this, look at, use these 4 steps. When it's about submitting your work, it's all about this. That's all I care about. Okay? But what I'm saying is, perhaps there's a statement, for instance, in the first problem set that is false. But in the exam, I might give you the correct version of it. Okay? So these are all sort of parts of the game. Any comments or questions? This also ends up being very important for literacy purposes too, because it's like, imagine, for instance, reading a novel in your native language, right? Even if you see a typo, you can figure out what they mean. But if you're learning a new language, sometimes what happens is you see a typo and like you're just like, it breaks all sense. And so you have to somehow take that into account. Of course, this is like a more postmodern perspective, but in our day, modern mathematicians essentially accept that there's probably a lot of mistakes in anything published. And we read things with that understanding. Okay? Any comments or questions about any of this? Okay?
So
Yes?
would you like us to write down when we perturb the statement in our solution that we turn in?
No.
Okay.
You can keep it to yourself, yeah. You can, okay, let me put it this way though. Anything that you submit that makes me think, makes our grader also think that you've actually spent time, is going to be helpful, both for you and for us to be able to grade things. Okay? So maybe you cannot actually come up with a proof, but at the very least you can say that it is correct. And you're not guessing it. You're sort of like, you made some experiments and like you sort of tested out certain cases, and it seems like it is correct. You can't actually prove it exactly. Or maybe it's like you figure out, oh, this works, this way works, but the other way around doesn't work and stuff like that. You're not going to get extra credits. But if push comes to shove, it'll be helpful in general, I would say.
Thank you.
I think your colleague also sent me an email. It's like, are we allowed to, talk to each other when we're doing problem sets? Certainly, okay? But it should be your own work. It was you, right?
Yeah.
Okay. And of course, as I was writing that answer, I thought to myself, what does it mean that it should be my own work? Because somehow the beauty of mathematics has also to do with its anonymity. Okay, so to whom does this statement belong? It belongs to everyone in a sense. Right? So you cannot just say, oh, this is mine. There's no such thing as copyright in math, for better or worse. Okay? But somehow, perhaps, that's sort of like a philosophical question. But one thing I could say, perhaps, is that when I try to describe what I understand, I hope you get the sense that, in a sense, I own what I'm talking about. Like, I know where things come from and stuff. That's what I mean when I say it should be your own work. Okay? You should be able to internalize it. So you get to talk to other people, discuss all that stuff. But ultimately, if I pull you, out on the street, ask you, you should be able to stand your ground. Okay? This is again sort of iffy or kind of vague of a statement, but hopefully as time goes by, we're going to come to an understanding. Is the light bothering you, by the way? Okay. Yeah, I realized. Better? Yeah. Sorry. Okay. So, and that's going to be an exercise. Exercise is to figure out does this statement work in the other direction? In other words, if you were to assume that n is an integer, positive integer, such that 3n plus 7 is even, then n has to be odd. Okay? That's, yes?
Is that an E or the N symbol?
Say again?
Is that supposed to be E or N is N? After the N, there's for all N, yeah.
In?
E. N.
Yeah. In integers, okay. I guess you mean this. So this is a set of integers. I use a subscript greater than or equal to 1. Okay? So 1, 2, 3, whatever. Okay, so we had proved this. We had proven this using direct proof. Let me perhaps reiterate the idea, and then we can perhaps write down all three of them. So maybe like so. First one was the direct proof. Second one is, what was it? Proof by contradiction. And then the third one is proof by contrapositive. By the way, the names of these methods don't really matter that much for us. Okay, I'm just telling these for sort of general common knowledge purposes. These are sort of logical things. I will keep using them so that when you're reading statements and reading proofs, you have some tools to parse statements. So how did you do the direct proof? I used a bunch of words, but let's just look at the structure. And what did we say? Before, what I said was, this whole thing is P, and this is Q. Okay? Another way of parsing the same statement would be to separate the quantifiers and think of n odd as P of n. This is a statement that depends on an unbound variable n, and call this Q of n. That's another way of parsing the same statement. Say n is odd, right? We assume P, then we keep pushing. Odd means n is not divisible by 2. In other words, the only possible way it can be not divisible by 2 is, well, if you divide it by 2, you have a remainder. But the only way that can happen is that if that remainder is 1. Okay? So there's a k, it's an integer, such that n equals 2k plus 1. I just use a definition of a number being odd. Then I plug it in to this thing. So 3n plus 7 equals 3 times 2k plus 1 plus 7 equals 6k plus 10 equals 2 times 3k plus 5. Then I say, as k is an integer, so is this expression, 3k plus 5. So k is an integer, hence 3k plus 5 is also an integer, hence 3n plus 7 is an integer multiple of 2. And that is the end of the proof. Okay. This was essentially the same thing as what I wrote last time. Last time I used more words. It's up to you, okay? You can use more words if you don't like the logical symbols. You can use less words if you want to be more concise, but you gotta use something. Okay? Yeah.
Can you define what is a quantifier?
So this is what is called the logical quantifier for all and there exists. Yeah. Okay. Any comments or questions about this? Okay, so now let's switch over to proof by contradiction. What was the change here? Now I'm going to assume both the hypothesis and not the conclusion, right? I'm saying, say the hypothesis holds, but the conclusion doesn't hold. And I'm going to try to get something that is clearly false. So say n is odd, but 3n plus 7 is, well, maybe you can write it like this. Say both n and 3n plus 7 say n is odd and this 2 is odd. Okay? I'm assuming P and not Q. And I want to come up with some sort of contradiction. What I can do is this. I can say, again, there's an integer, k, such that n equals 2k plus 1. This is using the definition of n being odd. But again, by using the same argument here, also, 3n plus 7 equals, by the same calculation, this. In other words, 3n plus 7 is even. But we also assumed that the same number, 3n plus 7, is odd, but there is no integer that is both even and odd. Okay. That is simultaneously even and odd. Okay. So it's almost like these are pretty much the same idea, and they are indeed the same idea, but formally they are different arguments. Okay. So the thing that is clearly wrong is this. I came up with this, and by hypothesis, in my new hypothesis, since I'm already assuming that this new number is odd, my argumentation tells me that there's a number, that there's an integer that is both odd and even simultaneously. And that's the thing that is obviously wrong in this proof by contradiction. Okay? Any comments or questions about this? the time. Third, then, proof by contrapositive. This time, I'm going to assume not Q. So now I need to assume that this guy is not even. In other words, it is odd. Say 3n plus 7 is odd. Then there's an integer L such that 3n plus 7 equals to L plus 1. Now I'm going to rearrange. OK, so let me remind you as well. I assumed not Q. I'm going for not P. In other words, I'm trying to conclude that if 3n plus 7 is odd, then n has to be even. OK, that's what I'm going for. So 3n equals 2l minus 6. Two times L minus 3, in other words. And so this says that 3n is an integer that is divisible by 2. It's an even number. Okay. Then from that, I can conclude that n, in fact, has to be even. Okay. Any comments or questions about this?
How did you get from the 3n equals 2l minus 3 to assume that 3n is even?
Because I was able to write 3n as 2 times an integer.
Do you avoid dividing by 3 just so that it ends up all being integers? Some 2/3 term? At the end?
Yeah, in a sense. You are, in fact, right in being skeptical about this part. There's a gap here.
I mean, yeah, I know it's true, but
Yes, but how would you sort of perhaps justify this? How to justify going from 3n is even to n is even?
an odd times an odd is an odd. Odd times an even is an even, so n must be even.
You can do that, yes, exactly. Does this make sense? So what your colleague is suggesting here is that if I wanted to be a little bit more careful in my proof, I would sort of open a sub-proof here and really prove going from here to there. Okay, I'll leave that to you. So exercise, there's a gap here. From here, you get there. Okay. You can argue like your colleague suggested, even, odd, whatever, the product, all that stuff. Another thing you can do is you can use essentially the main theorem of arithmetic, fundamental theorem of arithmetic, they say. If the product of two numbers is divisible by something, and if one of the factors doesn't divide it, then, or rather, one of the factors is not divisible by the factor, by the product, or by this factor, then the other one has to be divisible. Another way to do this, in other words, is to say, can refer to the fundamental theorem of arithmetic. So any integer can be written as a product of prime numbers, all that stuff. You can do that too. Okay. Now, one of the things that you're going to notice in this class is when it comes to formal argumentation, there's always some amount of gap in your arguments. You cannot just say, you cannot give every single step. So you're going to have to eventually sort of take larger and larger steps. Okay, this is going to happen. And part of the class, and I think some of you are already sort of having this issue, you're going to be somewhat paranoid. You're going to say, oh, was this enough? Should I have proven this step, that step, whatever? That's going to be part of the game as well. Of course, what should be proven and what you can expect your audience to know depends on the context. So something could be something to be proven in a class, but then when it comes to professional mathematicians talking, clearly, even though one of the sides perhaps doesn't quite know the proof, by just listening, people will just take your word for granted. Because eventually you sort of start developing a sense as to whether or not certain things are correct. Okay? And really at the high level, you really don't worry that much about things that everyone pretty much agrees is correct. You just stop wasting your time. Because there are many other things where people actually argue if this is valid. Okay? Okay. So in a sense, I guess what I'm trying to say also is that in week 1, I was talking about logic and stuff like that, and that's something like the grammar, and that's how you're supposed to be doing things. But there's also how people actually do things, more descriptive way of sort of describing math, and this side is more closer to the descriptive way. I'm trying to give an accurate sense as to how modern mathematicians do math. And this is not to say that you're all going to be mathematicians, of course, but at the very least, you should have an idea as to what it entails when someone says, I'm a mathematician. Okay. Any comments or questions about these? So these are the 3 methods. There's one more method I mentioned, induction. We're going to talk about it later this week. What I want to do now is I want to describe the relation operations with relations. Now remember, what was the point of a relation? The point was this, we're really interested in these things called functions, but then I said sometimes something could look like a function without it actually being a function. In that case, it's probably something like a relation. So a relation for us is basically a generalized function. So relation operations. Need to take a couple of things. So definition. What do I need? Okay, I think this is going to suffice. Let x, y, z be 3 sets. Let me also let A be a subset of X. And then I want to have 2 relations. I want one relation, R, let's say, from X to Y, and another relation, let's say, S from Y to Z. And with these objects, I want to define certain things. Domain of R is a certain subset of X, defined like so. The notation for this is dom of R. Okay? This is a set of all those X's. Remember, this is the set builder notation, such that for some Y in Y, XY is in R. So this is the set of all those X's such that the relation R relates to some y in y. Okay. By the way, a very common notation for relations is also, instead of writing this pair xy is in R, we just write x, R, y. This is the same thing. Okay. This is also fairly common. So you say x relates to y via R. One of the things, of course, you can imagine perhaps is that, let's say you have a family gathering. One relation would be everyone is related somehow. But then you could say relation S is the relation of being a sibling. Okay, you could do something like that. Or you could say relation F is the relation of being the father of. You can imagine things like this. So that's the domain. Image of R is M of R. And basically it's the other way around. The set of all those y's and y's such that some x in X is related to Y through R. That's the image. What else do I need? Oh, inverse, okay. Let me be a little bit more clear here. I'm going to call it relational inverse. R to the minus 1, this is denoted. Okay. And instead of looking at xy's, you're going to look at yx's. So now, R is a relation from x to y. R inverse is going to be a relation from y to x. Y comma x in y times x such that xy is in R. Okay. I'm going to say a couple more words about this in a second. Composition. Of R and S. So far I haven't been using S, now I want to use it. So I'm going to denote this composition by S, O, R. And now this is going to be a relation from X to Z. You get rid of the middle term. The set of all those X comma Z's in X times Z, such that for some Y in Y, XY is in R, and YZ is in S. Okay. What else do I need? Restriction. R is technically a relation from X to Y, but whenever you have a subset of, let's say, X in this case, you can restrict your relation so as to only focus on what R does to A. And so this is denoted like this. R, you put a bar like this, and then you put a subscript A. R restricted to A. And so this is the set of all those x, y's in R, such that X is in A. Okay. One final thing. I know this is a lot of definitions. We're going to be done with these formalities soon. Image of A under R I'm going to denote by R of A, okay? And this is nothing but the image of this restriction. And combining this with this, what is this then? It's a certain subset of y consisting of all y satisfying this property. Because I'm looking at this restriction, I'm going to take x not in capital X, but in the smaller set A. In other words, y in y such that there is an A in capital A such that AY is in R. Okay. That's a mouthful. There's a bunch of definitions. I'm going to keep reminding you of these definitions. The main punchline here is that all of these definitions in particular apply to functions. Okay? I should also mention, last week we were talking about these two words, input and output. At this point, I think we can sort of identify the word domain with inputs in a sense, and image with outputs in a sense. Okay. Yeah.
You have two dots. What does it mean?
That's short for such that. Yeah. That's why I'm sort of using a bar here. Yeah, so perhaps we can sort of turn this into simple English to parse it out. What is R of A? A is a subset of X. Okay, R is a relation from X to Y. R of A is going to be a subset of Y. How is it defined? It is defined as a set of all those lowercase y's in Y, such that for some A, lowercase a, in uppercase A is related to Y through R. That's one way of sort of turning into simple English.
So the bar is such there, or the dot?
Bar is also such that. Yes, and in fact, in the textbook, they use colon here too, I think. I'm using this bar notation as sort of like a set builder notation. But ultimately, sets are nothing but logical statements too underneath. So. Okay. Oh. All these. Also apply to functions. I'm going to leave it to you as an exercise that if R and S are relations that are graphs of functions, then it is also the case that this composition relation is the graph of a function. If R and S both are graphs of functions, what does this mean? Remember, this is a specific technical term. It's this abstract vertical line test. I'm saying R and S both satisfy the abstract vertical line test. I'm saying the exercise asks you to show that in fact this composition relation, it's a relation in and of itself, too satisfies the vertical line test. of a function. And of course, this function is denoted by the composition of the associated functions. So maybe I can write it like so. So if R is the graph of F and S is the graph of G, then S composed with R is the graph of G composed with F. How many of you have seen this function composition stuff? Okay, many of you, yeah. You have about 5 minutes. Another thing, okay? Relational inverse is always defined. For any relation, r to the minus 1 is a well-defined relation. It's an okay, it's a well-defined object. In particular, you can look at the relation that is the graph of a function and look at its relational inverse. It is not the case that the relational inverse of a function that is the graph of a function, again, it is not the case that a relation that is the graph of a function, when inverted, still remains the graph of a function. Warning. To summarize what I was trying to say, I want to say this. Typically, f to the minus 1 for a function, okay, really stands for graph of f to the minus 1. In other words, f to the minus 1 typically is not a function itself, okay? It's possibly a relation, even though f itself is a function. So may fail to be a function. Okay. I'm going to leave it to you to come up with perhaps examples of these ideas. I want to sort of reiterate this. One example, of course, that would be really good here would be something like f from R to R, and here's another notation, x sent to sine of x. Do I have time? According to my clock. 1 minute, okay. We're going to keep talking about this example, what f inverse means, or f to the minus 1 means in this context. But that will be it for today. Thank you, and I'll see you tomorrow. Okay, let's start. Good morning. So today I'm going to take attendance. We're going to discuss this example that I mentioned last time. There's some new notation here too I would like to introduce. Then I would like to discuss this fourth common proof method, which is called induction. And after that, probably we're going to be done for the day, but for the rest of the week, we're going to be focusing on certain properties of numbers that we're going to need to use in this class. So if you look at the textbook, they do a bunch of things. They, for instance, construct integers out of natural numbers and so on. So we're going to bypass a lot of those sort of abstract constructions because ultimately, technically how the reals is constructed from the rationals, while important, it ends up not being that useful, at least for the purposes of calculus. So I'm going to take a more pragmatic approach. We're going to sort of bypass that. I'm going to sort of put into certain statements these certain properties that we're going to keep using. And then by the end of this week, I hope to be able to cover these important notions, namely supremum and infimum. These are sort of one of the, or a few of the main ideas in more rigorous mathematics that we end up needing to use. So here's a attendance sheet. I want you to put your last name and the first name and then signature or initials, something like this, okay? Okay. So this was the example that we were looking into. So whenever I write something like this, f colon from something, arrow to something else, this means that this is a function. This is supposed to be a function, in other words. Now, it might happen that I write it like this, or you write it like that, and somehow this thing that you allege to be a function fails to be a function, but that's going to be an error. Like, I'm never going to use this notation for something that is a relation but not a function. And so typically you would say, probably you're used to this notation, you would say f of x equals sine of x. So this is one way of writing it. I'm going to use this barred arrow notation. This is what that is called. So you describe where your set is from and to. And also, you also say, using this barred arrow, where your function is supposed to take an anonymous input to which value. So I'm saying, so writing this is the same thing as this. And if you want to be more formal when describing the function using this more classical notation, you will want to say something like this. I.e., f is the function from R to itself defined by f of x equals sine of x for any x in R. Okay, you can write it like so as well. Okay, and at this point you can also think about what sine should mean in this context. Clearly, I'm just taking it from single variable calculus. Okay. So these kind of things we're gonna not worry too much about how to define sine and stuff. It's defined exactly the way it was defined before. And so, for instance, in the textbook too, you're gonna see in the first chapter especially, they sort of prove things like x plus y equals y plus x, where x and y, let's say, are integers and stuff. There's certainly something to be proven, but again, I'm just going to bypass the proofs of matters like this. Okay, we have more important things to cover. I'd rather we focus on these more important calculus-like aspects as opposed to the fact that, addition for numbers is commutative and stuff. Okay. Okay, so, and again, let's remind ourselves, when we're thinking about functions, really we're thinking about the shapes that are the graphs of the functions. Right? These are essentially identical for us. The rule that is the function and the shape that is the graph of the function. And how does this look? Certainly it looks like this. I'm not going to draw the whole thing. Okay. I guess it's better to first draw the asymptotes. Like something like so. And then like this. Okay, that's 0. Then looks like so. And so this is the graph of the function. Apologies for the picture. Okay. Of course, there are certain numerics here. This height is 1, this height is -1, for instance. This is 2 pi, this is 4 pi, and so on. It's a standard sine function. And of course, we're typically thinking of x as the horizontal and y as the vertical. Now, we're going to be, I told you, looking into things like f to the -1. Now, f to the -1 is not a function in and of itself, okay? But it is a relation. When it comes to inverting relations, graphically what you're doing is you're imagining its shape. Let's say x is the horizontal axis and the y is the vertical axis. Now you're going to take the shape and reflect it, or take its reflection along y equals x, so as to replace y axis with the x axis and the x axis with the y axis. Okay? So let me reiterate. Okay, so if I were to take the shape and reflect it along y equals x, what does it turn into? It turns into something like so. So again, let me draw these. So now this is y, this is x. So I guess it should be like so. Okay? So this new shape, you see, it's a relation still, but it's not a function. And why do I get to say that? Because I can use this abstract line test, or the concrete line test if you want. For instance, if I were to look at y equals 0, okay, I realize that this specific vertical line hits f to the -1 at infinitely many points indeed. Okay? Fails vertical line test, hence f to the -1 is not a function. Okay? It exists. It's a well-defined mathematical object. However, it's not a function. Now, one thing you're going to see is that even though f to the -1 fails to be a function, for instance, we are going to see notation like so. F to the -1 of x. Maybe I should say y. F to the -1 of y. And when you see this, okay, this again doesn't mean that f to the -1 is a function. This is where things get confusing. Technically, this actually stands for graph of f. This is this relation to the -1, and then the set that consists only of y. Meaning, opening this up, this really means the level set. X in R in this case, so the input space. Maybe I should just use capital X here to not confuse. Capital X, such that f of x equals y. It's a level set. Okay. Of course, it is the case that if f is an invertible function, in other words, f to the -1, the relation, 2 is the graph of a function, then this level set ends up being consisting of only one point also, in which case we just use that pre-image or point. Okay. So these are sort of notational sort of matters. Maybe at this point, you don't see you don't really see the point, but point of me mentioning all this. But I'm just letting you know these kind of things do show up every once in a while. You're going to get confused. I'm just letting you know. Okay. In a sense, you're right in getting confused. It's kind of confusing. Any comments or questions about this? Yeah.
So for f inverse the relation
Yes.
related to sine of x, can we write it f inverse of sine of x? Would that be correct?
Yes. Yes. But probably you want to say something like this. So when you say, so I guess you're asking for this. Yeah. So probably this is a valid way of writing things, except probably you want to say something about this x being fixed. Okay. So maybe you want to put x0 here to signify that this specific x0 is a specific input. Yeah. Okay. So opening this up, this means this is a set of all those x's, real numbers, such that sine of x equals sine of x0. And of course, if you want to be a little bit more clear as to what this specific level set means, this is nothing but 2 pi translates of x0, right? Because sine is supposed to be periodic. You can write it like so as well. 2 pi n such that n is in integers. Right? This is probably a lot more useful of an expression. But this is a perfectly valid way of writing things. Any comments or questions about this? Okay. Now, I want to now talk a little bit about this mathematical induction business. So this is the fourth method of proof that we're going to use. It looks slightly different than the other three that we discussed. And typically, we use this method of induction when we have a family of statements indexed by, let's say, integers. So, proof by mathematical induction. And before I even mention this, I wanted to mention something else. I think one of you in the last class asked something about me writing this. And then I think I corrected this, but I think the question was about this. Yeah, as I was watching the recording, as I was editing, I realized. So technically, this is also an epsilon or an e, whatever. Okay. So if you want to use, instead of this specific e, if you want to use actual e, that's valid. And in fact, in old literature, you would see the symbol. Instead of this, people would use this. I think what happened eventually is that people realize, oh, this gets kind of confusing, whatever. And then they realize, oh, I'm just going to use this stylized e for element of. Does this kind of answer? OK. There was a question somewhere. No? OK. So this is just like a notational matter. OK, proof by mathematical induction. This time, I want to have a claim of the following form, let's say. For any n, let's say, starting with 1. 1 is not necessary, but this is like a standard way of writing things. P of n. Okay. Now this is a logical statement that depends on one variable n. Then you prove it like so. Induction has two steps, okay? The first step is what is called the base step, or the anchor step. Show that for the first index, P holds. In other words, show P of 1. And then the second part is what is called induction step. Now you assume for some arbitrary n, P of n is correct. Assuming this, then you show that the statement P also holds for the next integer, P of n plus 1. So assume P of n, well, let me say, show P of n implies show for any n integer, P of n implies P of n plus 1. There are different versions of this induction statement, induction proof. There's something called strong induction, whatever. Let's not get into these. This is the vanilla version of the mathematical induction. For most purposes, this is going to suffice. Okay. So for instance, here's an example. The classical example of this is, well, the sum of integers and stuff. So just to reiterate, question?
I was just asking if that was a 1 and a semicolon, the z.
Yeah, greater than or equal to 1. Yeah. Yeah. Yeah, so this is typically for sequences, let's say families of statements parameterized by integers. Okay. So in a sense, it's more limited in terms of its form. So the standard example of this, for instance, is something like so. How many of you have seen this notation before? Okay, pretty much all of you. So for those of you who haven't seen this, this is basically a for loop, and this is a summation. This basically says, the left-hand side is the sum of all k's, where k goes from 1 to n. Okay? If you want to be more explicit, you can just write it like so. One plus 2 plus 3 plus 4 plus dot, 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 all the way up to n. You start from the lower limit, you go all the way up to the upper limit. This is pretty much like a discrete integral, if you want. Okay. So, how to prove this? Well, let's use a mathematical induction proof strategy. Again, parsing the statement. So as you note here, the only thing that is free is n, right? So P of n is this equality. So this whole thing is P of n. So, two steps. Base step. Let's first say we'll use mathematical induction. By the way, I'll say a word about why I'm using this word mathematical here in a second. Base step. What do I need to do? I need to first look at the first index. In my case, the first index is 1, so I'm going to put n to be 1. Then I just look. Left-hand side is the sum from 1 to 1. This is just 1. And then the right-hand side is when I plug in n equals 1, what do I get? 1 times 2 divided by 2, which is 1. Left-hand side matches with the right-hand side. So I can say, hence, the statement is true for n equals 1. This is the base step. Typically, in induction, the base step is going to be fairly straightforward. OK? Any comments or questions about this so far?
So that's the left-hand side?
Left-hand side, right-hand side.
Right. You plug in. Can you show that?
Well, I mean, this is by definition the sum of all integers from 1 to n. If n is 1, yes. Well, I mean, I agree. But this is the legalese part, OK? This is how you legally argue in math. I agree, though. So for instance, if I were to, I mean, I would never ask you to prove something specifically using mathematical induction. But even if you had chosen to prove something using mathematical induction, if you didn't write this base step, I would not deduct any points, OK? In this class, even though formalism is important, I'm never going to sort of punish you for not being very strict. Okay. I'm just letting you know this is how you're supposed to do these kind of things formally.
I can understand right-hand side, you plug in 1 at the place of n.
Yes.
But the left-hand side, what does that symbol mean?
So this symbol,
Yeah.
the sum of all integers from 1 to n. When n is 1, it's only 1. The sum of all integers from 1 to 3 is 1 plus 2 plus 3.
Right.
The sum of all integers from 1 to 2 is 1 plus 2. Then if it means something, the statement, the sum of all integers from 1 to 1, it has to mean 1. No, I understand. Like, I understand the worries. We're just playing some sort of a game here, but maybe in computer science this kind of makes sense.
It's like we're kind of breaking down something obvious, but in just to make sure we're clear on what we think is obvious.
Yeah. Yeah.
Why did you plug in 1 for k? I think that's like, why is the left-hand side 1 in this case?
Well, I mean, this is the expression in question. I cannot plug in k equals 1 here. Because k already is sort of like a dummy variable for this expression. Okay? And so by definition, this has to be the sum of all integers from 1 to 1. What can it be? The only thing it can be is 1. Yeah. I mean, I understand the worries, OK? And I should also mention, in practice, when the base step is as clear as something like this, people would not even write this. they would just write the induction step. Any other questions about this? OK, so now I want to do the induction step, and that is the more important part. Now I need to assume for some arbitrary n, P of n is correct. OK, that's what this says. Assume, right? So this is a sub-proof if you want. I'm going to assume for some n, or for any n, this is true. And I need to show somehow that P of n plus 1, 2 is true. So K is n times n plus 1 divided by 2. I'm assuming this. I need to show the same thing holds when instead of n, I see here n plus 1. We would like to show, I'll write it here. Continue from here. We would like to show that k from 1 to n plus 1, k equals n plus 1, n plus 2 divided by 2. And again, you don't need to explicitly write down what you're trying to do. But even when you're sort of trying to figure out the proof, it might be good to write things down explicitly to remind yourself what you're trying to do, and perhaps also to your audience also. OK. So the point here is that now, because I assume this is also something I can use. So I'm going to start with the left-hand side again. OK. Sum from 1 to n plus 1 I can split as sum from 1 to n plus the n plus first term. Maybe I can write it like so. OK, just split this. But then instead of this, I can use this expression, because that was something I assumed. Let me put a dagger here. Dagger. Instead of this, now I have n times n plus 1 divided by 2 plus n plus 1. OK. Now we keep going. We need to consolidate terms. Of course, I can factor out the n plus 1 here. In fact, let's do that. If I were to factor out this n plus 1, I have n divided by 2 plus 1. But then this is nothing but n plus 1 times n plus 2 divided by 2, which was what I had claimed. OK. At this point, you're done, and you could say something like, hence, by the principle of mathematical induction, we're done. Again, this is not something you have to write, but if you want to be more clear, you can do so. Any comments or questions about this? Yeah.
So you, from this step right after the dagger, you factored out the n+1.
Yes.
And then what did you do after that to get the n+1?
I consolidated this term. Instead of 1, I wrote 2 divided by 2, and then I put the fractions together.
Okay, sounds good.
Yeah. Okay. Any other comments or questions? Now, I write it like this too, and maybe I should be a little bit more clear. This is the right-hand side then. You don't need to write every single step here, for instance. You can skip a bunch of them and so on. This is like a personal matter. I, especially as I'm sort of trying to explain things in class, I try to write as many steps as possible. But the number of steps you need to write down, there's no such thing as, you have to write this many steps, whatever.
Why'd you write the plus in parentheses under that?
Where?
The dagger.
The dagger.
Oh, it's
Here? Or?
no, the blue.
This refers to the fact that I use this specific assumption. This dagger refers to this equality. I'm saying, oh, this is in my pocket, and here exactly I'm using it. In this case, it's not that confusing, of course, because maybe using something like this is confusing. But as time goes by, we're going to have 7 different hypotheses coming from 5 different steps in the proof. And then we're going to use 3 other theorems that we proved before. So that's going to be where the documentation comes into play. Yeah. Any other comments or questions? Yeah.
So the math step, can you point out?
Well, the math step is here. I did the math here. If you want to be a little bit more clear, you could say something like this. The general proof was mathematical induction, but in the induction step, I technically used a direct proof. Okay. There was a question somewhere over there. Okay. So why the word mathematical induction? Because induction really means the more sort of intuitive idea. But back in the day when people were worried about the validity of arguments like this, there's still debate, by the way, but we just assume it because that's the standard nowadays. But philosophers would argue things like, oh, I have never seen any white pigeons, and therefore there are no white pigeons. That would also be a case of an induction, but that would not be mathematical induction because technically you cannot see all possible pigeons alive. And so that would be incomplete induction and so on. And so what we do in math is, we just use more words, which somehow gives us more validity, at least in our eyes. Okay. Of course, you can just use the word induction here. Any other comments or questions about this? Now, you could argue here. So let's now try to perturb the statement a little bit. Try to look into the claim. This is the end of it, and certainly this proof verifies that this claim is correct. But what it doesn't answer is how we came up with this formula to begin with. Right? How do I know this formula? Well, you could say I did some experiments. I said, oh, I'm just going to add integers from 1 to 5, 1 to 6, whatever. And then I sort of tried to come up with a formula. And that was the formula that I was able to think of. And now, after I have a candidate for a formula, for a closed formula like this, I go ahead and I use the mathematical induction to verify mathematically that this is indeed a true statement. You can do it like this. Another way to do it would be to perhaps try to come up with a direct proof of the formula. And again, you could use experiments and stuff like that for this, but here's, for instance, the standard direct proof of this claim. Maybe I should ask you, do any of you know how to prove this directly? Just by taking integers, bunch of them, add them up, manipulate, and get this. You know it?
Don't know if I could recite it off the top of my head, but I've seen it before.
Okay. Exactly. So the story goes, there's this very famous mathematician, Gauss, and he was a prodigy and everything. And back when he was a child, he was taking a math course, and his professor gave the whole class the task of adding integers all the way up to 1,000, whatever, so that they would be occupied. And then Gauss, him being the genius that he is, he figured out the formula, and then he just plugged in n equals 1,000 and computed this thing, and then it was like, went out to the garden or whatever. I don't know if this is accurate, but this is something people say. So the idea is this, okay? So, so let me again remind you, this symbol means this. Oh, by the way, to answer your question again, if I wanted to bypass this issue of adding integers from 1 to 1 being 1, I could just define this expression to be equal to 1. I can do that too. So I take this, okay? Now, if I were to take 2 of these, okay? But you see, what I'm going to do is, instead of writing it in an increasing fashion, I'm going to write it in a decreasing fashion this time. Up, and minus 1. Plus 1. And then if I were to add everything up, I would have twice the sum on the left-hand side, and on the right-hand side, you see I can combine this and this, and then this and this, and then this and this. In other words, I would have n times n plus 1. Hence, on the right-hand side, I have a total of n many n plus 1s. And so if I were to take that 2 to the other side, I get the formula also. That's another way of proving the same thing. Okay? This would be a direct proof. Okay? Now, here's something interesting going on. Earlier, when we were looking at these different proof methods with this arithmetic statements, the idea was pretty much the same in all of the proofs, even though formally they are different. Here, I hope you would agree with me, the idea behind induction and this direct proof is very different. Mathematically, these are different things. This, in a sense, I would say, involves more insight as to the integers and how they operate and stuff. Okay? So throughout, we're going to see examples of this. We're going to be able to talk about different proofs, mathematically different proofs of the same statement sometimes. Any comments or questions about these matters?
You say that induction proof is based on direct proof.
Not necessarily. What I did say was, in this specific case, in the induction step, I used a direct proof. But if you wanted, in the induction step, you could have used proof by contradiction, whatever. Yes. Any other comments? I think I have about 10 minutes. Okay, let's try to perturb this statement a little bit more. What else? Maybe I should ask you. Now that we have this verified, what else can we do with this? How can we perturb this statement? Any guesses? Think about sort of like claims that are similar, perhaps.
There's another sum formula for k squared, the sum of terms from k1 to n of k squared.
Yeah, so your colleague, probably you've seen something like this before. Yeah, so based on experience, your colleague suggests, well, instead of this k, why don't I use a different exponent here and try to come up with a similar formula on the right-hand side? Okay, that's one way of looking into this. Of course, you can go further and say, instead of 2, 3, 4, whatever, what if I were to put an arbitrary polynomial here? Polynomial in k, and then the right-hand side would change too, probably. And can I sort of figure out how that would change? Okay. I'll leave it as an exercise. Let's say for any n and for any p, well, I can write it like so. This is a well-defined expression. It's in fact a function of n and p. Let's call it sum n p. I'm defining. Exercise is to find a closed formula for this specific function s of n comma p. Formula, closed formula. Okay. To reiterate, when I say something like this, okay, find something. In this class, that means find it and also prove it. Prove that it is correct. Okay? You cannot just compute something in this class. This probably is going to be hard. Let's just do Sn2, second exponent. Okay. I should also mention the standing of an exercise. So these are things, these are exercises that I give in class. These are not things that you need to turn in. Okay, these are things for you to do on your own. We can discuss them certainly, either separately or perhaps in class if it's too important or important enough. What might happen is I give an example in class, and then the same example, rather, I give an exercise in class, and then maybe a version of this exercise shows up as a problem in a problem set, or it might also show up in an exam. Okay, So you are responsible in that sense, but I'm not going to ask you to submit anything about these. Okay. Okay. Any comments or questions about any of this? Yeah.
In this Pn,
Yes.
previously you wrote summation of k equal like full, right?
Yes.
That equal sign, is it the same as this one?
So you're asking if this equality is the same thing as the equality I use, for instance, here. 1 to the p plus 2 to the p plus dot 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 plus n to the p.
Yeah.
Yes.
It doesn't imply.
No. This equality, if you really think about it, is a definition. I'm defining this as this. And here too, I'm defining this as this. Yeah. Yeah, some people, for instance, use this notation. They will put equality and then colon here to make it asymmetric so that this is clear now that the left-hand side is being defined as the right-hand side. And here too, they would put this. But this is not very common. So I'm not going to use it. If you're welcome to use it, of course. Okay, I have a couple minutes. What do I want to do? Okay. So now I want to mention the following, and we'll be done with today. Number systems. Okay. So before I describe these sets or introduce them as just sets, of course, these expressions as sets, but certainly we're using things like addition, exponentiation, whatever. These we're just going to take as granted. So we have a couple of things, right? Positive integers, let's say, and then this turns into, let's say, all integers, and then this turns into all rational numbers, and then this turns into all real numbers, and then this is transformed to the extended reals. So these are all the sets of numbers, or the major ones that we're going to use. This keeps going, of course. There are complex numbers, quaternions, and stuff like that too, but we're not going to use these. More complicated things. These are going to be the main actors. And these come with certain operations, addition, division, whatever. And somehow, each next step in this sequence of sets, or sequence of algebraic systems, somehow can be thought of as a better version of the previous one, okay, in terms of these algebraic operations, and then eventually in terms of calculus properties. We're going to talk about these tomorrow. Thank you. Okay, let's start. Good morning. So today, I'm going to say a couple words about these number systems. Now, if you look at the textbook, in the textbook, they go more into detail as to how you go you go from one number system to the other one and so on. We're going to bypass most of these ideas. What I'm going to do is, after sort of introducing these number systems, I'm going to give you the 4 important provable axiom / theorem I say here regarding numbers. Okay? So why do I say provable axiom / theorem? In principle, because these are going to be things that we can actually prove, but in order to be able to prove them, we need to sort of discuss these number systems in more detail. What we're going to do instead is that we're just going to take these statements as axioms and be on our way, because for calculus purposes, these things, these four statements, really do act as axioms. At the end of this class, if there's still time, I'm going to say a couple more words as to how to sort of change these number systems, one from the other one, how to go. But that's not going to be very important for us. That gets rather abstract as far as I'm concerned. So that's going to be it for today. And then on Friday, we're going to talk about the most important matter when it comes to these foundations, at least for our purposes, namely these two ideas of supremum and infimum. Somehow, these two notions end up being closely related to these, at least one of the four statements. Before all that, though, I wanted to make a correction. Yesterday we were talking about this expression. So I'm imagining sine to be a function from the reals to itself, and I fix a specific input value x0. And we talked about how the sine to the -1 is really not the inverse of the sine function. This is the inverse relation. This set really represents all those x values whose sine is equal to the sine of x0, whatever that is. And yesterday I gave this equality, but when you think about it, this is not quite correct. This is a subset. I should add something here. So union x1 plus 2 pi n, where n is an arbitrary integer. The point here being is that, so let's just look at one phase here. Okay, this is one part of this sine function. And once you fix an x0, say it's over here, right? And then you look at the height. And then you need to consider all those other points whose height is at the same level. But then you see, if I just look at this set, I'm just going to look at the 2 pi n iterates, or 2 pi n translates. But there's other ones that I'm missing over here. Okay, so this x1 is this x1. So you need to be taking translates of this x1 as well. So somehow x0 plus x1 divided by 2 should, for instance, in this case, give you some integer multiple of 2 pi plus pi over 2. I'll leave it to you as an exercise to explicitly write down a formula for x1 in terms of x0. In other words, x1 really is a certain function of x0. Is a function of x0. And your task in this exercise is to find one expression. There is no unique function that relates x0 and x1, because this is not the only choice. In fact, I could use some other translates if I wanted. But it's one. There's at least one. It's not that important, of course, for our purposes, these kinds of matters. And so here are the essential number systems. Back in week 1, I introduced these as essential sets. But really, when we're thinking about these kind of matters, it's not just sets, but it's set with additional stuff. And so the story goes, well, you start with integers first, okay, or positive integers. And really, when we're thinking of positive integers, it's not just some set, but it has certain functions defined on it. One of them is what is called addition. The other one is multiplication. Okay. I think in the textbook they don't give a name to this algebraic structure, but if you want to use a word, you could call this a semi-ring, for instance. So in the field of algebra, or abstract algebra, I should say perhaps, people end up being more interested in the axiomatics of these algebraic operations. We're just going to take them for granted because they're not really our concern. But the point is, you start with something like this, and then you say, I want to turn these operations into much better operations somehow. In the following sense. For instance, if I just look at positive integers, certainly I can add 2 of them, but I cannot subtract. In the sense that if I knew only positive integers, I wouldn't be able to make sense of -2. And because of this, you switch over to the next system. All integers, somehow you describe all integers using only positive integers. You still have addition and multiplication. Maybe I should be clear here. You have addition and subtraction now. Subtraction and multiplication. And maybe instead of this dot, I can use an x, like this, multiplication. So how can we sort of describe this transition from here to there? Well, you want to sort of include additive inverses, you would say. If you have 5, you also want to have -5. So want additive inverses. Then you keep going. You say, OK, I have additive inverses. Now addition and subtraction works really nice. But now I have another operation here, multiplication. And I would like to be able to likewise divide also. That's technically what is called a multiplicative inverse. By the way, this now becomes a ring. So now you focus on this multiplication, say, and then you say, I want to include divisions as well. So for instance, if I knew only integers and how to add and subtract and multiply them, I wouldn't be able to make sense of 1/2. But certainly, we like these kind of things. So then you go over to the rational numbers, plus, minus, times, and division. Now you include the division, OK? And this is technically what is called, this structure is what is called a field. If you've taken linear algebra, or if you're taking linear algebra, this is the field of scalars, so to speak. There are many others, but this is one. So here you say, want multiplicative inverses. Oh, OK. And then in the next step, really where calculus comes into play. Somehow, at this point, you're done with sort of making the algebraic operations better. But still, you say to yourself, well, this time, I'm sort of thinking of perhaps geometry, basic geometry and all that. And I would like to be able to say, you say, well, take a right-angled triangle with each side of equal length. And I want to think of the hypotenuse to be a certain length as well. And I want that length to be a number. But alas, it turns out if you look at this, the length of this side is not quite a rational number. And in fact, that's something we're going to prove. OK? But √2 is not a rational number. You cannot write √2 as the ratio of two integers. OK? So you could perhaps imagine a calculator. Certainly a calculator calculates this for you. It gives you a rational number, but certainly that's an approximation. It's not actually √2. OK? And so once you include all such numbers, and how can we perhaps imagine these at this point? These are basically all those numbers that you can approximate arbitrarily well using rational numbers. Then you get reals, again with the same operations. But now you have what is called completeness. Okay? And this is going to be one of the 4 axioms that we're going to keep using in this class, completeness of the reals. And then you go one step further, and then you say, well, once I start doing calculus, every once in a while I get this infinity symbol, and somehow I would like to be able to make sense of this infinity symbol as basically a very large real number. So let me just say, want plus or minus infinity as valid values. And from that, you get this extended reals. There's, again, some addition, subtraction, multiplication, division. And typically, even though you could sort of do operations with infinity and minus infinity as numbers, there are certain technical issues. It's not going to matter if you allow operations with infinity or not. But we'll talk about it if it does show up. Okay. So this is the sort of progression. And technically, this class, even though it is called Foundations of Analysis, you really should think of it as Foundations of Real Analysis. So we're really focusing on these. You could, in principle, go even further, perhaps from here, switch over to what are called complex numbers. There's analysis with that. But the flavor of that type of analysis is rather different. It's a different class. I mean, I would suggest that you take it eventually, but that's not what we're doing. Okay, you can do calculus with complex numbers. If you sort of take something like this, the extended reals, switch over to the complex world, complex numbers, then it turns into something like complex geometry, perhaps, or Riemann sphere and things like this. Again, you can do these kind of things. Alternatively, from here, instead of going to reals, you can do this completion differently. Then you get something called p-adic fields. You can again do calculus with the p-adics. Flavor is completely different. We're not doing that either. Okay? So we're doing real analysis. This somehow is the most intuitive one, and this is the one that matches with what you learned in calculus. Okay? Any comments or questions so far? And let me say how you go from here to there, for instance. In all of these, at the end of the class, if time permits, I'm going to mention more specifically what exactly you do mathematically. But the point is this. I didn't tell you this because we're not going to use it. But just like you can multiply sets, you can also divide sets. Technically, you divide a set by what is called an equivalence relation. And so using this procedure of dividing a set by an equivalence relation, it turns out that we're able to emulate, for instance, an integer using 2 positive integers. So how could you perhaps talk about -5 without actually using minus? Well, you could say 1, 6, 1,6, with the understanding that 1,6 actually stands for 1 minus 6. Okay. The problem, of course, is that 1,6 is not itself -5, because what is 2,7 then? It should be the same thing. So that's where the division comes into play. Okay, this dividing by equivalence relationship business. So I'll just say this. So the idea is always switch to the more complicated system by emulating. Okay. So divide set by equivalence relation. I'll mention a little bit at the end of this class what formally this means. Again, this kind of gets abstract, this emulating things by other things and so on. It turns out that in higher math it is important, but somehow not necessarily for us. We can safely just like forget about how to construct things and so on, and then just focus on the axioms. Somehow, because it doesn't help knowing how to construct this from this to do actual calculus. So in the textbook, you'll see words like Dedekind cuts and stuff like that. Okay, these ultimately they're important, but not for calculus purposes. So that's why I'm skipping. Okay, so first I want to talk about these 4 important axioms/theorems. First one is what is called the well-ordering principle. Well-ordering principle. It says this, okay? It's going to sound quite possibly something, it's going to sound very obvious, but this is how you do formal math. It says that any non-empty set of positive integers has a unique minimum. In other words, let S be a subset of positive integers if S is not the empty set, right? This was my notation for the empty set. If S is non-empty, then let's try to think about how to write this unique minimum business. Well, here's how I can write it. There is a unique S, let's say, star in S, such that for any S in S, S star is less than or equal to S. Let me reiterate in words. Any non-empty set of positive integers have a unique min. Has a unique min. Fairly self-explanatory. For instance, technically this is equivalent to the principle of mathematical induction. Oh, go ahead.
Is the star just a way to denote that the variable?
Yeah, I just like picked something, yeah. I'm going to typically sort of put a subscript star to say, oh, this is like a specific one. Yeah. What I was saying is, technically this is equivalent to the principle of mathematical induction. In other words, whatever logical system we're using that allows us to say mathematical induction is a valid proof method also means that this is an axiom that you can use. We can spend time proving the equivalence of these 2 things, but I don't see the points. Okay, I'd rather sort of switch over to more calculus-like matters. So that's the first axiom/theorem. Second one is the completeness axiom. Okay, I mentioned it over here when we switch over from Q to R. There are a couple of ways of saying this. Let's say it like this, perhaps. Any non-empty set of reals that is bounded from above has a least upper bound. Is this how I said it? Yes. Let S be a subset of reals if S is non-empty and is bounded from above. I'll mention what this means in a second, more specifically. But if you can guess what it means, probably you're right. Is bounded from above. Then it has a least upper bound. Okay. So I want to mention this. I want to give a proof of this claim over here that I made earlier. This is an important matter. The point of this second axiom is that it's exactly the thing that separates these two things. Okay. Let's for now take for granted that root 2 is not a rational number. Okay. Here's how this second axiom distinguishes rationals from reals. If I were to look at this set, Q in Q, such that Q squared is strictly less than 2. Okay? This is a set of rational numbers. Certainly, it is non-empty. For instance, 0 is in there. Okay? And it is bounded from above. For instance, if a rational number is in this set, it cannot be larger than 10,000. Okay? There are many upper bounds. Okay? But you see, if I were to ask, is there a least upper bound? Is there an optimal upper bound to the set as a rational number? That would require that root 2 is an available thing for me from the perspective of the rationals. But assuming that root 2 is not in rationals, we wouldn't be able to say that this set has an upper bound within rationals. Switching over from rationals to reals exactly solves this problem. Okay. I'll say more about this. Ultimately, the supremum has to do with this completeness axiom also. Let me state the other two axioms as well. They are more sort of self-explanatory, and then we'll focus more on this completeness axiom as well as the proof of this. Third axiom is what is called the Archimedean property. It says this. There are again a couple of ways of stating this. The way I like to state, well, let's leave it like this. The way I think the way they state it in the textbook is like so. Any real admits some integer that is greater than it. In other words, for any x in R, there is some integer n such that x is strictly less than n. Okay. The way I would like to imagine this is sort of dividing everything. And so instead of saying any real number, so for any real number, there's an integer larger than it, I'd rather think of the following. I would say for any real number, there is a rational number of the form 1 over n less than it. You can think of it like that as well. But then you would need to quantify this, of course. Let's not worry about that. This is much more straightforward in a sense. So that's that. And then the fourth axiom is what is called the density of rationals. This basically says that between any two real numbers that are distinct, there is at least one rational number. Okay. For any, well, we can state it like this. For any positive real, let's say, there is a Q in Q such that Q is strictly between 0 and x. Okay. These are the 4 axioms that we're going to keep using throughout this class. Okay, we're going to say, oh, this, that, the other thing. Why? Because of this axiom. Okay. Any comments or questions about this? Intuitively, we could imagine any real number. Oh, go ahead.
Is the Q in there exists a small q and a q, is it the same as the rational numbers Q, or is it just?
Yeah, exactly, yes. Very good. Yeah, this is my attempt at writing Q in the blackboard bold. And this was the rational number. So this is the same thing as this symbol. Okay. Now, intuitively, we can imagine any real number to be some number that you can write using this decimal notation. Possibly, though, of course, you should allow on the right-hand side of the what do you call it, the dot, non-repeating patterns, so that you have irrational numbers as well. You want to be able to think about like pi and e and root 2 and all these things. And so in that sense, then, I can imagine any of these x's, any real number, as maybe something like this. Right? So x is, there's a bunch of zeros, but then you have a bunch of digits to the left of the dot. You have a dot, and then you have a bunch of digits that possibly go to infinity. Okay? 1.23, whatever. I hope this kind of makes sense, because if I had something like this, what I can do is I can get rid of the decimals and then increase the first digit by 1. That would certainly be an integer. And that would essentially satisfy this Archimedean property. This is not a proof. I'm just trying to justify that this is somewhat of an obvious statement, in a sense. It's something believable. Okay, does this make sense? So for instance, I take the number pi. If I take x to be pi, I want one integer larger than it, 4. Okay. I'm not saying there's a unique integer. I'm saying there's at least one. Okay. How about here, density? And again, what I can do is, let's say I take a positive real number, again, pi, let's say. How can I come up with an integer that is strictly less than it, but still positive? Well, I can just get rid of the decimals. Pi turns into 3. 3 is a rational and integer. But even if I had started with 3 itself, then I can just look at 3 over 2, for instance. I can just divide by 2. Okay. Any comments or questions about these? I realized, axioms like this, it kind of maybe looks like pointless, but I guarantee you that we end up using these over and over in this class. Yeah, go ahead.
Could you re-explain what you mean by least upper bound?
Yes, that's where I'm going to switch over to now.
Oh.
Yes. So the more contentious issue, I think, is this too. This is where things get complicated. First, though, I want to prove this statement. Okay, that's a claim we should prove. This is one of the first examples of a proof that pretty much everyone sees. Typically, that was the first example that I had seen proven sort of formally in school. Yeah.
Before you erase it, now here, square root of 2 is not q.
Yes.
Then you point to the blue color, what do you mean?
I wrote this statement as I was talking about different number systems. This, I said, is one of the reasons why we switch from Q to reals. But then I kind of said a couple words about this completeness axiom. And what I said was, what really distinguishes Q from reals for our purposes is this completeness axiom. And this was supposed to be an example for why. I'll say a couple more words about what this bounded from above means, having a least upper bound means, and then I hope it's going to make more sense.
You said the q, little q,
Yes.
is in that set, right?
Yes.
Square root of 2 is in, it's not in that set.
It's not. Yes. I'll mention more. Take this on the side. First, let's focus on this. Verify this. So that's the claim. Root 2 is not a rational number. The standard proof of this is, it goes by proof by contradiction. You say it is, and you sort of get into some complications. Let's say for a contradiction, that root 2 is indeed in rationals. Well, by definition then, that means that root 2 can be written as p over q for two integers, p and q, where q is non-zero, because otherwise it doesn't make sense, right? So there are p and q in Z, q not equal to 0, such that root 2 equals p over q. Okay? Rearranging, I have that p equals q times root 2. Taking squares, I have p squared equals 2 times, hence let's say p squared equals 2 times q squared. As q is an integer, so is q squared. And this is pretty much the only thing trick that we've been using so far. This basically says that p squared is an even number, even integer. It's divisible by 2. So that p squared is an even number. Okay so far? Go ahead.
You're saying it's an even number because it's
Divisible by 2. Yeah. Yeah. This is why this is the first proof that a lot of people see, because you just use odd and even. Here's the tricky part that I'm going to leave to you. If p squared is an even number, then p2 has to be an even number also. again by this even times even whatever. I'll leave that part to you. Exercise. P2 is an even number. Okay. If P itself is an even number, then that means P squared is divisible by 4. If that is the case, if this is divisible by 4, dividing everything by 2, I get that Q squared 2 is an even number. Hence, P squared is divisible by 4. So that 2 times Q squared is divisible by 4. Just to reiterate, this really comes from this by blue star If that is the case, dividing everything both sides by 2, I get that Q squared is divisible by 2. In other words, Q squared is even. By the exercise that I left to you, the same argument also shows that Q is even again. By the exercise, Q is even. And the final step is to say, well, all this is fine and dandy, but in principle, I know that when I write something like this, P over Q, I could have simplified the numerator and the denominator so that they don't have a common divisor. Go ahead.
So is the exercise you're giving us part of the proof or something separate?
Yes.
So this isn't a complete proof then?
Yes.
Okay.
Yes. I will almost never give a complete proof. Okay. There's always going to be like gaps. Math is not a spectator sport, unfortunately. Q is even. But then one could have chosen P and Q so that they don't have any common divisors. Of course, except one. And that's a contradiction. Okay. I feel like you're not happy with the fact that I'm leaving gaps in the proofs. One thing, okay, I'll do this one. How would I argue for this? I could say this is a sub-proof in the bigger proof. Use another contradiction. Say P is odd, but it's squared. Square is even. Okay. Okay. So P is 2k plus 1. So P squared is what? 2k plus 1 squared. and then you open this up. And what do you get? You get 4k squared plus 4k plus 1. This is an even multiple. This is a multiple of 2. I'm saying this is 2 times some integer plus 1. In other words, p squared is odd. And so that's the proof of this exercise, for instance. Does this kind of make sense? Okay. I would suggest to you that while I'll do this, this is not going to help you. Me sort of telling you this is how you do it. This is how I would do it. Because somehow it's like I've done this like many times, and at this point I don't even think about it. But you need to go through it yourself. You're going to realize it's not quite the same. Any comments or questions about this? Now, you might be like me, and you might not like this divisibility shenanigans. Okay? If that is your psychological makeup, I would suggest something like this. You could try to turn this proof into more sort of symbols. So for instance, instead of writing this in plain English, you could say, oh, there's an integer k such that p equals 2k. That's the same thing as saying p is an even number. Okay? And then from here you would say, oh, but then p squared is 4 times k squared. That's what it means for p squared to be divisible by 4. Okay? You can sort of, that's why I sort of introduced all these logical matters. If verbiage sort of makes it more complicated for you, you can just turn everything into simple logic to parse the argument that is being handled. Okay? Any comments or questions about this? Go ahead.
The 4k squared plus 4k plus 1, what did that turn into?
Oh, I just said I didn't worry about collapsing these. I said, oh, this is 2 times some integer. I just put a star here.
Oh.
Yeah. I was lazy. Okay. Okay. So you see the perspective kind of changes as well, because typically you would sort of open this up and write this explicitly, but I don't really care what this number is specifically. It's some arbitrary thing anyway. All I care about is that it's an integer. Okay. So part of this class is also going to be sort of cutting corners in a very sort of thoughtful manner. You're going to think about, oh, do I actually need to compute this specific thing, or can I go around actually computing x, y, z? That's going to be part of the game also. Any other comments? I have a couple minutes, 4 minutes. Probably I'm not going to talk about this set division business. I'd rather spend more time on this bounded from above business and least upper bound. So, this is all I care about for now. Okay. This property. Let's clarify what it means for a set of real numbers to be bounded from above. Let S be a subset. Let's say it's also non-empty also. Well, S is bounded from above if for any S in S, well, let me put it this way. There is some number, let's say M, that is greater than any S in S. If there is an M real number such that for any s in S, S is bounded from above by m. Okay. Now, I should note that writing these quantifiers the other way around, in other words, saying for any s in S, there's an m in R, such that this happens, that's not quite the same thing. I want one number that works as an upper bound for all s's in S. Okay? So for instance, integers satisfy it the other way around. Okay? It's very important. The orders of these quantifiers are going to matter for us. Because we're going to have, for instance, something like continuity and then uniform continuity. And then somehow, ultimately, the only difference is where you write the quantifiers. And you even switch one step further. We're not going to talk about it in this class, but you go to what is called equicontinuity. Again, you just like change the change where you write the logical quantifiers. Okay. Okay. 1 minute. Now, in words again, let's say what this means. S is bounded. I didn't write. Is bounded from above. If this statement holds. If I can find some number m that is greater than or equal to any number in my set that I started with. It's an upper bound. Okay. Least upper bound is going to be the optimal upper bound, in a sense. I'm out of time, though. We're going to talk about that on Friday. Thank you. OK, let's start. Good morning. So problem set 1 is due tonight, and problem set 2 is almost ready. I'm going to release it later today. Today, our aim is going to be to discuss this completeness axiom a little bit more. This is really one of the most important axioms. Remember, we had 4 axioms that essentially govern numbers for us. And this is basically what sort of distinguishes real analysis from other types of analysis. We're going to discuss certain definitions related to this, boundedness and so on. And then we're going to try to perhaps turn this statement of the axiom into a logical statement, just so that we have some practice. And then I'm going to define these 2 important notions, supremum and infimum. We can, at this stage, say supremum is basically something like a maximum, and infimum is something like a minimum, but somehow notions of maximum and minimum, they're not well defined in every single situation, even though we're going to see these are well defined pretty much always. And are there any comments or questions before I go ahead? So let's review this notion of boundedness. I think I gave only this. So if I take a subset of real numbers, right, I'm going to call this set S to be bounded from above if there is a number R such that for any S in S, S is to the left of R. And what is this trying to say? It says this. If you have this real line, let's say this is positive infinity and this is negative infinity. Of course, I can imagine S to be just a bunch of points. Right? Maybe there's like a piece of an interval here, whatever. This whole thing, let's say, is S. I call this to be bounded from above. Well, if the points in S, if they don't run off to infinity in the positive direction. Right? So I can just put a stopgap here. That's the idea of an upper bound, or bounding from above, right? Something like this, upper bound. One thing that is important is that, for instance, let's write it explicitly. Let's say S is something like, well, 0, 1. Let's say open, in fact. I'll ask you this. Is this bounded, first of all, bounded from above? It is bounded from above. What's perhaps an upper bound? 1 is an upper bound, but it's not the unique upper bound, right? 2 is an upper bound, 3 is an upper bound. I don't really care. Pi is an upper bound. Boundedness from above doesn't say anything about uniqueness, which I hope it kind of makes sense, because it's kind of hard to imagine, at least in the real setting, to have a unique upper bound. There's at least one. That's the point. OK? And if you do the same thing from the other direction, you have the notion of boundedness from below. Now, instead of worrying about running off to positive infinity, you worry about running off to negative infinity. And if you're able to stop that behavior, that's a lower bound. OK? And so, for instance, this open subset, this open interval, is both bounded from above and bounded from below. So, for instance, I can say, so upper bound, 5, lower bound, minus pi, whatever. Bound minus pi. That's fine. But for instance, if I were to look at something like this, let's say S, let's say is the set of positive reals. OK? Using interval notation, I can write it like so as well, if I want. This, for instance, is not bounded from above. It runs off to infinity. But it is bounded from below. OK? And I'm going to call a set bounded if both happens simultaneously. S is bounded if it is bounded from above and below. OK? And here's a nice exercise. It's not very hard once you get the hang of these logical stuff. A subset S in reals is bounded if and only if. This was something that I used in the first problem set as well. And I mentioned what this means. Maybe I should ask you, what is this if and only if? If with 2 Fs. Right? So instead of saying this, I can just write this. In other words, when you see if with 2 Fs, that means if and only if. In other words, using standard logical verbiage, you can say this really establishes what is called a necessary and sufficient condition. Or you could say, much more simply, this statement implies this, and vice versa. OK? This is a nice exercise. I will leave it to you. I'll say one thing. More than sets of real numbers, in this class, we're going to be interested in sets of functions taking real values, typically defined on an interval, but it's not really that important where the function is actually defined for most purposes. So let's say, I'll just add a small definition here. This one comes right after this one. Maybe I should say this is definition star. This is an addendum to star. So let X be a set. And let's say curly f is a collection of functions defined on X taking real values. Remember, this was the set of all functions from X to R and I'm just taking a collection of functions. This curly f is just a bunch of functions now. It's a set of functions. Okay, later on we're going to look at, for instance, continuous functions, integrable functions, and so on. But for now, I'm just taking an arbitrary collection. Or maybe I should, before going into that, we can talk about this as well, but let's not go this far first. Let's just say I'm just taking one function. Okay, let's not worry about the collections. Let's just take one function. I'm going to call this function bounded from above, below, or bounded if its image is so. Is, let's say, bounded if, well, f of capital X, which really means the image, is bounded. I had defined this notion, image, or the image of a set, for relations. I told you everything that you define for relations apply for functions as well. But if you want to be a little bit more explicit, you can just write it out using the set builder notation. This is nothing but the set of f of x's such that x is in capital X. For any lowercase x in x, once I apply f to this lowercase x, now f of x, by definition of f, is a real number, which means that this is a set of real numbers. So that definition you can import immediately to talk about the boundedness of this specific set. Okay? So a function is bounded if its image is bounded. Maybe we should give an example to this as well. If I think about something like this, for instance, well, our first example was x mapped to sine of x. This is a bounded function. What is its image? Its image is the closed interval -1 to 1, because sine just oscillates between 1 and -1. This is a bounded function. Okay. However, for instance, I can look at, let's say, positive integers, positive reals sent to reals, x sent to 1 over x. This is one part of a hyperbola. Right? Its graph looks like this. This is the graph of f. You see, the image of this function is all positive real numbers, and consequently, this function is not bounded. Okay? Any comments or questions about this? Yeah.
Is that set the f of x such that x is in x, is that for the f of x equals the image or for the earlier set?
This is equal to this, which is equal to also this.
Okay.
Yes, very good. I'll add one more notation here. Instead of looking at arbitrary functions from x to r, if I'm only considering the collection of all bounded functions, I'm going to put a subscript here, and I'm going to write capital F sub b. Okay? So f sub b, x semicolon r, this is the set of, or the subset of all functions consisting of all bounded functions. Okay. We'll talk about this later. So for instance, one of the major theorems in week 4, I think, after we discuss sequences and after we define continuity, will be that any continuous function defined on a closed and bounded interval is automatically bounded. This is what is called the maximum principle. Any bounded function, any continuous function defined on a closed and bounded interval attains its max and min. So for instance, I can imagine 1 over x to be defined on this. On this, it's not bounded, and it doesn't attain its max. But this is not a closed interval, for instance. This is an open interval. We're going to talk about all this later.
Any comments or questions so far?
So you
semicolon.
This?
Yeah, what is that?
I mean, this I had actually defined before. This is an instance of this third way of defining a new set. I said if you have two sets, we can talk about the set of all functions between the two sets. So this means this is a set of all functions from x to reals.
So in between is what? Dot? Or?
Here, semicolon. Some people just use like a comma. It doesn't really matter. I typically like using a semicolon to separate in this situation. Any other comments or questions? OK. So now, with all this said, let's go back to the completeness axiom. It says, again, any non-empty set of real numbers that is bounded from above has a least upper bound. OK. So we discussed, I gave you the definition of what it means for a set to be bounded from above. Now we need to figure out what it means for it to have, for a set to have a least upper bound. In a sense, maybe we can look at this example again. 0 to 1, open. I said, for instance, 5 is an upper bound, 6 is an upper bound, 6 times pi is an upper bound. So in essence, upper bounds are unlimited. But in a sense, you can try to optimize it. What is the best upper bound? Well, it's the most frugal one. In this case, it will be 1. OK? And so this least upper bound really refers to that. If you have an upper bound, you have a best upper bound. OK? And to reiterate, as a real number. I'll give an example for this in a second also. So that means that if you have a bunch of points in the real line that somehow you can stop from running off to infinity, there's a stopgap. You can push that stopgap as far as possible, and there's a certain sort of limit, so to speak. There's always a specific number. So now let's try to turn this into a logical statement. Using logical quantifiers and so on, let's try to write this. So for any s, which is a subset of reals, okay, I need to have some assumptions. First, I want to say that it's non-empty, right? S is not equal to the empty set. Non-empty. I need to say it is bounded from above. What am I going to do? I'm going to just write this. There is an R in R such that for any S in S, S is less than or equal to capital R. These are my two assumptions. Then, well, now I need to turn into logic this existence of a least upper bound. So I need to say something like this. There is an upper bound, and it's the optimal one. Then, there is, let's use perhaps the letter beta. There is a beta in R such that, first of all, I want to say that this beta, this number, is an upper bound for S. Okay. But furthermore, I also need to say that this beta is the best upper bound. It's the optimal upper bound. And how could I say that? I could say something like this. If I had some other upper bound, this beta is less than or equal to it. For any beta bar in R, and for any S in S, oh, this should be S, of course. If S is less than or equal to beta bar, then in fact beta 2 is less than or equal to beta bar. Now when you turn more intuitive statements into logic, often you're going to perhaps see some sort of like redundancy here, but this really is needed. Okay. I mentioned all this logical stuff so that if you start getting confused about what certain things mean, you can sort of think about how to parse everything, turn it into logic. And for some people, somehow writing things like this sometimes helps. I'm not saying it's going to help all of you. I benefited when I was first learning analysis, being able to sort of use logic, turn everything, just like parse the grammar of what is being stated. So that is to say, you don't need to, so I'm not going to ask you, oh, look at this statement, turn it into logic, whatever. But it's something that some of you might feel, might see some use. Okay, go ahead.
What's the B bar mean? Beta bar?
I'm saying it's like, so this is part of choosing the notation somehow. In my mind, what I'm saying is beta is an upper bound, and beta bar is sort of like an alternative upper bound. For any other upper bound, I'm saying beta is better than this other upper bound I chose. There was another question somewhere. Okay. And this is the negative side of logic, of course. When you write things down like this in logic, what does this even mean? Why are you even looking at this? Right? That's the sort of bullet you end up needing to bite. And so you're going to see throughout, even though I'm going to keep using logical symbols in class, I'm not going to just read this word by word or symbol by symbol. Right? I'm like, as I'm writing something and as I'm reading something, I'm already interpreting what it should mean. And this is also something that's a skill that you have to develop. Just like, for instance, when you're first learning a language, you're probably reading letter by letter and then word by word, and then eventually you start reading sentence by sentence and you sort of get the point. Right? There's a similar thing happening here. Any other comments? Or yeah, go ahead.
Sorry, in the beta is less than or equal to beta bar. Why would the beta be lower than the beta bar if the beta is the better upper bound?
Because beta is closer to S in a sense.
Oh, okay.
So upper bounds can grow larger and larger. So there's nothing stopping you from taking larger and larger upper bounds. But in order for an upper bound to be better, it should be as small as possible. It should be as restrictive as possible. Yeah. Go ahead.
So that kind of confused me. So in that example right there, where that open interval from 0 to 1, you're saying 5 could be an upper bound
5 is an upper bound, yes.
in that open interval?
Yes. I'm not saying 5 is an upper bound in that open interval. I'm saying 5 is an upper bound of this open interval.
Oh, okay.
I mean, this is how you do math. Like it resonates with me what you're going through right now, and this is how you do it. This is how you sort of establish things from the bottom up in a rigorous fashion. Any other comments or questions? Let me think. Here's a logical exercise again. This ends up being very useful, okay? So part of why I wrote it like this is that throughout this course, we're going to have, oh, here's this bizarre set, and its least upper bound is this, or whatever. Or we're going to have like multiple sets, and somehow we're going to have to manage, oh, the least upper bound of this set is less than the greatest lower bound of this other set or something. So we're going to have to worry about these bounds quite a bit in this class. Analysis, in a sense, is all about these inequalities. And so what ends up happening is, well, sometimes you need to sort of actually compute or come up with certain expressions as to what upper bounds of certain sets are, okay? And so a logical statement like this, in my experience, becomes helpful because this is an actionable sort of thing. You can, oh, this is like a claim that I can perhaps try verifying or disproving. So this exercise that I'm going to write down is yet another thing you can use. Oh, I'm not going to erase this. I would rather erase this. The exercise is this, okay? Let S be non-empty and bounded. Let's say bounded from above. And I'll give another exercise. Now, at this stage, whenever you see something like this, I'm telling you, you can just assume this, okay? There's nothing to prove here. For us, there's nothing to prove because we didn't spend time constructing the reals. I'll again mention, say a couple words about this rationals not having this property, but let's leave that for now. This statement that you always have a best upper bound, least upper bound, you can just take for granted. And in this case, in this exercise, whenever you see this, you know that this least upper bound exists. Okay. First, even before the exercise I had in mind, I should say, first exercise is that instead of this a indefinite article, you can turn it into a definite article. In other words, in terms of logic, there's a unique least upper bound. Okay. So, in other words, I can put here an exclam. Okay. In fact, I'll write it like this. That's an exercise. The exercise I had in mind here is this. And denote by beta its least upper bound. Oh, I don't want to say it like this. I should say it like this. Then, let's say we use beta there. Maybe we can use a different letter. Then gamma is the least upper bound of S if and only if, equivalence again. Well, I'm going to keep the first statement. For any S and S, S is less than or equal to gamma. And instead of saying this 2, what I can say is this. Any number smaller than this gamma fails to be an upper bound. And how can I say any number less than gamma? Here's our first use of the letter epsilon. Epsilon is always going to be for us a small positive number, but we're not going to logically state it's a small number. For any epsilon positive, there is an S such that gamma minus epsilon is less than S. This is very useful. And I highly recommend that you verify that indeed this gamma being the least upper bound of S is equivalent to these two statements. Now, what is the idea behind the second one? Well, initially what we said is this, right? So we have one upper bound, and this beta is the best upper bound. In other words, if I were to take an alternative upper bound, beta would be a better upper bound. On the other hand, this says this. Beta is an upper bound, and if I try to, or in this case, gamma is an upper bound, and if I try to use any smaller number, gamma minus epsilon, that's going to fail to be an upper bound. In order for something to fail to be an upper bound, it must be the case that at least there is one point in your set that is greater. Okay? This is really coming merely from logical shenanigans. But somehow, in my experience, I use, instead of this a lot more. Your mileage may vary, but I thought I should mention it. Okay. Any comments or questions about this? Go ahead.
Is it strictly less than, or is it
Yes.
separate to be in the?
That doesn't quite matter that much because here this saying that there's for all epsilon does a lot of work underneath. I like using it like this. In my experience, having this strict inequality here works a lot faster, improves.
My question is, doesn't that open the possibility for it to be the greatest number in the set, and so not an upper bound?
What do you mean? Sorry, ask again.
So if there's not an equivalence there, doesn't that open the possibility for S to be in the set?
Equivalence where?
Second row at the end, gamma minus epsilon less than S.
Okay.
I'm wondering why it wouldn't be less than or equal to S.
That's because I sort of verbatim negated the logical statements. Because in the definition of an upper bound, we use the less than or equal to. And so let's do it like this, okay? I'll write it here. So this statement really says gamma minus epsilon is not an upper bound. So this, I'll write it here. So gamma minus epsilon fails to be an upper bound for S. In other words, it is not the case that gamma minus epsilon is an upper bound for S. And so I can say, instead of saying, so what is the negation of this? Gamma minus epsilon is an upper bound for S. By our definition, you would write it like so. For any S in S, S is less than or equal to gamma minus epsilon. If I negate this, what this turns into is there is an S in S such that the other way around of this works. And when I flip this, this turns into, so we can write it like so if you want. This is a not operation. This turns into, there is an S in S such that S is strictly greater than gamma minus epsilon. Ultimately, though, it doesn't matter because if I wanted, I could have defined an upper bound to be a strict upper bound. Logically, that's a different statement, but for analysis purposes, it's not going to matter, actually. And so the gist of all this stuff is, if instead of having a strict inequality you like less than or equal to, you might use it this way as well. It's going to give you the exact same statements eventually. Okay. Does this kind of answer? Yeah, this is this bizarre thing about analysis in calculus in general. So somehow we're interested in bounds, but the notion of a bound intrinsically is something vague. So often we're going to worry about the fact that x, y, z is bounded, but we're not going to care that much about what that exact bound is. Okay? You're going to see more and more examples of this as time goes by. Any other questions? I want to give a couple examples. And then we'll talk about the supremum and infimum. And in fact, at this point, I can erase this as well, I think. By the way, I'll mention more about this negation later. Because typically what we're going to do is, we're going to say, let f be a continuous function. And then I'm going to say blah, 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 implies that f is in fact discontinuous. Then you're going to have to think about what it means for a function to be not continuous. And then you're going to have to sort of think about the opposite and stuff like that. A lot of the time, quite frequently what ends up happening is, if you have access to the logical statements, negating statements ends up being simply an algebraic operation. Here what I'm doing is I'm basically sort of distributing this negation over the constituents of this statement. We'll talk about all that later though. So example. Let's first establish this. Okay, let's for instance start with s equals 0, 1. Well, one side open, one side closed. Okay, remember this was the set of all those reals such that 0 is less than or equal to x, which is strictly less than 1. Okay. This set is non-empty. How do I know that? For instance, 1/2 is in there. It is bounded from above, like we discussed. 5 is an upper bound. By the completeness axiom, it has a least upper bound. The least upper bound of this is 1. Now that's a claim to be proven. Least upper bound of S is 1. It's a real number. So not only do I have existence, which is guaranteed by the completeness axiom, but I'm saying in this specific case, the least upper bound is this specific number. Okay? Now we need to verify two things. First of all, 1 is an upper bound. That's fine. So 1 is an upper bound. But you see, this is not enough to say that the least upper bound of S is 1. You also need to justify that indeed 1 is the best upper bound. It's the least upper bound. So we need to say something about the second item, either in this format or in the original format I wrote. Now I should ask you, perhaps we can come up with an idea. How can we justify that 1 is in fact the best upper bound for this specific set?
Proof by contradiction.
Okay.
Assume that there is some value less than 1 that's better, and put the contradiction.
Okay. So essentially using this. Okay. In fact, instead of going for that contradiction, I'll go for a direct proof because I want to sort of exemplify how one might use one of the other axioms that I mentioned. Okay. So I'm going to use this statement. Okay. I could say let epsilon be positive. Okay. Let's draw a picture. This is 0. This is 1. Well, I want to imagine epsilon, 1 minus epsilon to be somewhere here, OK? What I need is, well, one S in S. I need to be able to display some point here, in between these 2 points, ultimately. How can I do that? Right, so for any epsilon in for any positive epsilon, I need to be able to display some point in my set that exceeds this supposed upper bound. Okay, right? I want to show that this 1 is the best upper bound. I say, oh, let's say that there's a better upper bound. But I need to verify that somehow this fails to be an upper bound, really. And the only way that can happen is if there is a point that exceeds this upper bound. Go ahead.
Could you use the Archimedean property essentially to denote that? That's the idea we want to use that. I just don't know how you would apply it.
Yes. No, exactly. You're right, though. So what your colleague suggests is I can use this axiom called the Archimedean property. This was one of the 4 axioms I stated. It says, given any 2 real numbers, there's an integer between them, strictly between them. OK? By AP, Archimedean property, there is an S. In fact, it's a rational number such that 1 minus epsilon is strictly less than S, which in turn is strictly less than 1. Between any 2 real numbers, there is one rational number at least. But because this specific set, the set from 1 minus epsilon to 1, the open interval, is a subset of S, that means that this specific S that initially is nothing but in, it's initially in rationals, has to be inside S also. Okay, and so by Archimedean property, I can indeed verify this. And so that finishes the proof. Okay. Now the subtlety here is this, okay? A lot of the times, even though what we're trying to do is rather formal, it's going to be very useful to draw pictures. But this doesn't mean that at this stage, you should say, oh, for instance, what I was expecting you to say was something like this, for instance. Oh, there's this 1 minus epsilon 1, and then if I want to come up with some number in between, I can just take the average of them. Okay? In this case, it would have worked. But then I was going to sort of adjust the example a little bit so that certain things break. Okay? Does this kind of make sense? This is where sort of really things get, they take an ugly turn in a sense. Like I realize this. This is like a very different way of doing math from what you're accustomed to, probably. So, and being able to use this upper bound and also supremum and infimum, these are going to be related notions. It's going to take this whole course for you to get accustomed to. And so if you're feeling sort of out of place, that's perfectly normal at this point. Okay. Comments or questions? So let me perhaps say one word about the difference between then having a least upper bound and a maximum. In this case, this set doesn't have any maximum. It's not well defined. There is no greatest number here because one end is open. Okay? Supremum is well defined here. That's what we're going to say. This least upper bound, supremum, is well defined. It is 1. But the maximum of this set is not well defined. Okay. The remaining 7 minutes, I want to define supremum and infimum. Okay. Or perhaps even before that, I'll give another example, actually. This was this set of rational numbers I mentioned last time. Example. Let's call this time the set T. T, let's define to be the set of all those rational numbers whose square is less than 2. Okay? First of all, this is a set of real numbers. It is non-empty because, for instance, 0 is in it. T is not the empty set. Now I want to say something about it being bounded. But for instance, I can say well, certainly if x squared is strictly less than 2, x squared is also strictly less than 4, which would imply, by taking the square roots, that x is less than 2. And so x squared is strictly less than 2. If you want, we can use a different number, of course. 10, which means that x squared is less than 10, which means that x is less than, 100, which means that x is less than 10 by taking square roots. And so 10 is an upper bound. So T is bounded from above. It's non-empty, it's bounded from above, and it's a set of real numbers, because any rational number is a real number. Okay? By the completeness axiom, I am guaranteed that this specific set has a least upper bound. The claim, of course, is that the real number, square root 2, is the supremum of this. Least upper bound of this. Least upper bound of T is root 2. Okay. Now remember last time how we proved that this specific number is not a rational number. It's not in Q. What was the point of all this stuff? What was the point of this completeness axiom? It's this. In principle, you can look at the set and you can say, well, here I can think about certainly this set of rational numbers. Okay, I can take the square, whatever, less than or equal to, less than 2. That's also fine. So I don't need to refer to this more complicated thing, perhaps. I can make sense of this perfectly, even if I didn't know what the real number is. Oh, these are ratios of integers. But if I wanted a least upper bound, if I wanted to be able to optimize my upper bound, well, I would need to think about this bizarre thing from the perspective of rational numbers that really I can't make sense of. Saying that root 2 is not a rational number essentially means if someone knew only rational numbers and not real numbers, they wouldn't be able to make sense of what this is. Okay? The whole point of switching from rationals to reals is so that we can formally make sense of this, at the very least. Okay. So the number system of rational numbers, I can add, subtract, multiply, divide rational numbers. Everything is nice, So algebraically, rational numbers is pretty much the same thing as real numbers. What it fails, the system of rational numbers, is precisely this property of being able to optimize upper bounds. That's what it fails. And we say, because of this, because somehow in calculus upper bounds are important for us, and we would like to be able to optimize our upper bounds, we need to sort of do something about that. And the solution is to go from rational numbers to real numbers. Okay? I'm not going to say much more about how exactly that is done. There are, in fact, multiple ways of doing this. Because ultimately, this is why it's done. But how it's done ends up being not that important somehow. I told you the 4 axioms that govern numbers for us. If you learn how to use these axioms, when to refer to these, it's going to be more than enough for us. Okay? And then maybe if you end up taking a perhaps course in set theory or foundations of mathematics or something like that, maybe there they would go more into detail. Okay? Any comments or questions about this? By the way, it doesn't help even if I were to put here a less than or equal to. Again, of course, the least upper bound is √2. But again, it's not in the rational, so I cannot make sense of it if I knew only rational numbers, if I knew how to divide 2 integers only. Okay. I have a couple minutes, but I think I'm not going to push. Essentially, supremum is least upper bound, and infimum is sort of the analog of it from the left-hand side, from the lower bound perspective. We're going to define these formally on Monday, but you have essentially the idea of the supremum. So this is the same thing as least upper bound. Okay, that'll be it for today. On Monday, we have the Dr. King Commemoration Day, so no class, and we're going to continue tomorrow. Thank you.